Let's apply it for hydrogen atom. Okay, so hydrogen atom, so we have operator f of r. I want to compute the expectation value. Okay, all of you, most of you are in physics department. So f of r. Some people who are not in from physics. So this is basically the integral. D is a 3D integral. Fr psi r square, mod square. Okay, so this is a wave function. Okay, for ground state, this is ground state. This is 100 L N L M. Okay, so ground state is this. It's a non-dimensionalized ground state, which I think I did that in several lectures before. So we have it. So I need to do the integral. Okay. Now in 3D, dr is now. By the way, this is a spherically symmetric. Huh? It's spherically symmetric. So there's no theta dependence. If there is theta dependence, then you do the theta integral first, then go to r. Okay, but I want to just illustrate integral with r. But with theta also it can be done. No problem. We can just do it. So I want to compute r expectation. Okay, so if you recall, so let me just do it in the side. Dr will be 4 pi r squared dr. Okay, I hope this people who are not from physics, you've done this in your math course. This is dr, 3D volume integral. Fr is r, and mod psi square. I need to integrate basically take mod square. Is a real function, so mod is not a problem. Minus 2r pi. Okay, so pi has been pulled out. 4 pi r squared here and another r. So, but I make it r prime. So this is for non-dimensional stuff. I just make everything r prime. So dr prime, dr, so r prime. Okay, so what do I get? So this pi will cancel, but this force coming out. But there's a problem, no? I mean, there's a argument of integral is exponential is minus 2r prime, but inside is I mean the integral is dr prime. So you make a simple change of variable, 2r prime equal to, we'll call it s prime or s. Okay, so we just rewrite as 2r prime is your variable to integrate. So how many of them are here? There is a 2 cube and 2. So there are 16. So 16 is, I have to multiply and divide by 16. Okay. So by change of variable, I'm getting 1 by 16 outside. So I get 1 by 4. This is 1 by 4. And this part we can do by Gauss quadrature. Right? Because this is basically integral e to power minus s prime s cube ds prime. Okay, now how many points do we need? We can just do it 2 points, right? S cube with n equal to 2. I'm not doing the algebra here, but we can just. I mean, I'm not trying to do real mathematical integral, okay, and computational integral, but you can just invoke Gauss quadrature, and you get the whole answer to be 3 by 2. So this is the power of Gauss quadrature. So in fact, any function, you can make any r prime here, it will work. We just use more points if r is, I mean, this function is a higher power of n. Okay, so 3 by 2. Now we can also compute 1 by r prime. Okay, so 1 by r prime, you can just, well, I mean, instead of r cube is going to be r, because 1 r will get cancelled, and this is 1. Now we can see one interesting thing is that 1 by r expectation value or average is not 1 by average r. Okay, and this is r is not a number, r is an operator. So is expect. I mean, this is we get that. You can also compute the potential energy. No. So what is the potential energy? So U is in CGS minus E squared by R. Okay. So it's okay. Now, if a non-dimensional this is basically 1 by R. Okay. But in any case, you can put this R and is R prime R naught. R naught is a Bohr radius. Okay. So it is minus E squared by R naught, which is 13.6. Well, it's not 13.6. Sorry, this is R naught. 1 by R prime is 1. Okay, so this is U. Kinetic energy, I'm not. It's not. We can't use this calculation, but you can use virial theorem. Okay, so kinetic energy is half of that, which is going to be plus is positive 2 R naught. So total energy is kinetic plus potential. So you add these two, is going to be minus square by 2 R naught. Okay. So I hope I didn't make algebraic error, but this is 13.6 electron volts. Okay. Anyway, so whatever algebra you did in quantum mechanics, you can also do with Gauss quadrature. Let's end this topic with the third polynomial, Gauss-Hermite. So Gauss-Hermite gives you integral for quantum oscillator. Okay. So these are first four of this Hermite polynomial. Okay. I'm going to tell you orthogonal property in the next slide. So 4 of them, and we can plot them. So these are again functions which are growing very fast with x. See, it reaches 10 power 5 when x is minus 10. That is why we need to suppress it by e to the power minus x squared. Okay, these polynomials are growing very fast for large x. Okay, so let's look at the functional form. Is minus infinity to plus infinity. So a is minus infinity, b is plus infinity, and I do the integral, and fx is that function. Okay, so this is the weight function, which comes from the orthogonal property that it is e to the power minus squared hi hj. These are the Hermite polynomials dx. It is j's factorial square root 2 pi. Okay, so this is gamma j and delta ij. Weight and fc says, of course, is a weight is a root of hj, and wj will be this object. No, sorry, weight of roots of hn. Okay. So this is again Python will give you. You don't need to compute by yourself. So let's compute this function. This is infinity. So I need 3 points, right? But this is default. This is the weight function. So we need to worry about this polynomial, and we need the 3 points. Then equal to 3. The answer is this, and which is exact. Okay. Of course, in computer, it will compute one root pi. Okay? So you'll not exactly get 3 by 4 root pi, but if you get the value of square root pi and check, you'll find the answer to be matching up to 16 digits to precision. So computer will have error, of course, with the round of errors. That we can't avoid. I cannot get square root pi with a numerical computer. But let me also make a remark that this function there is a module called SymPy. I'm not covering in this course. So SymPy is a symbolic Python, which is like Mathematica. So with Mathematica, we are treating. So there you can get this kind of thing. So it will do it analytically. Okay, a symbolic Python. So X is this will be a symbol, so it can be done. You can read up. It's very useful module, but SymPy I won't cover. Quantum oscillator, we can again do exactly thing like what I did for hydrogen atom. So I'm not doing it right now, but you can just reproduce yourself. You can compute expectation value of x squared. You'll get as n plus half by 2. Of course, h bar omega is a dimension, which I'm not writing here, but okay, non-dimensionalized h bar omega is already taken care of by scaling. Kinetic energy is same as that, and total energy is sum of the two, n plus half h bar omega.